Hello students, I am Ms. Deepika Bhandari. Today I bring you the next learning episode in BSc Forensic Science on behalf of the content writers Dr. Vimal Rar and Ms. Tulika Banerjee on an important unit of the paper titled Technological Methods in Forensic Science, that is Neutron Activation Analysis. In this lecture, you will be studying about neutron activation analysis and its principle. You will also get to know about the instrumentation of this technique. In addition to it, you also will study about the advantages and applications of this technique and about its forensic significance. Lastly, we will wind up this module with a conclusion. Module 1 Introduction, Module 2 Principle of Neutron Activation Analysis, Module 3 Instrumentation, Module 4 Advantages of Neutron Activation Analysis, Module 5 Applications of Neutron Activation Analysis, Module 6 Forensic Significance of Neutron Activation Analysis, Module 7 Conclusion. Neutron activation analysis has in a few decades has become one of the most important methods for determination of minor trace and ultra trace elements in solid samples. The main advantages of activation analysis are its accuracy and sensitivity. Moreover, it is an independent method, that is, this technique is not subjected to the same systematic errors as most of the commonly used analytical methods are. The method is applied in the semiconductor industry, medicine, biology, criminology, archaeology, geochemistry and environmental studies or quality control. Neutron activation analysis is a sensitive analytical technique used for qualitative and quantitative multi-element analysis of major, minor and trace elements in samples. Neutron activation analysis offers sensitivities that are far superior to attain by other methods in the orders of parts per billion or even better. The application of this technique is also extensive, that around 1 lakh samples go through analysis procedures every year. The technique of neutron activation analysis differs from most other analytical techniques in the manner that it undergoes nuclear transitions instead of electronic transitions. The technique was discovered in the year 1936 by Hevesy and Levy. They observed that when rare earth metals or samples consisting of such type of metals were exposed to a source of neutrons, they turned out to be highly reactive. Therefore, they identified the perspective of using nuclear reactions on samples by measuring the induced radioactivity so as to facilitate the qualitative and quantitative identification of the elements present in the samples. The technique of neutron activation analysis is a nuclear process employed for the detection of the radioactive elements in the sample and their concentration determination with great sensitivity without the destruction of sample which is being analyzed. Neutron activation analysis does not consider the chemical form of a sample and completely focuses on the nucleus, thereby allowing the discrete sampling of elements. It permits identification and measurement of concentrations of elements which are present in only minute or trace quantities of concentrations, that is less than 0.01%, such as scraps of paint, which because of their size are not susceptible to techniques. Under appropriate circumstances, neutron activation analysis can also identify both large and small pieces of material by precisely analyzing their trace element concentrations. Such identifications rely on the fact that although concentrations of the major constituents of similar specimens such as 2 pieces of glass may be nearly the same, sometimes trace elements as impurity show a wide variation from one source to another. Dear students, after giving a brief overview of the neutron activation analysis technique, I will now be discussing about the principle on which the technique of neutron activation analysis is based. The principle of activation analysis is that a particle such as neutron, proton or alpha particle etc. or photon like gamma rays, Bremsstrahlung radiations from accelerated particles induces a nuclear reaction in an atom of a target element. Then the product is detected and quantified by photon or particle emission, or if radioactive, then by its decay properties. The method is based on neutron activation and thus requires a neutron source. To carry out a neutron activation analysis, the specimen is placed into a suitable irradiation facility and neutrons are bombarded onto the sample, allowing the elements to form isotopes. After the specimen has been irradiated with the neutron source, decay of the artificial radioisotopes takes place with the emission of gamma rays or particles being characteristic to the element from which they are emitted. For each element, the radioactive decay paths and emissions are known, thereby allowing the study of spectra of emissions of the radioactive samples and determining the concentrations of the element present in it. Every discussion on instrumental technique is incomplete if we do not understand the instrumentation and working of the procedure, and hence with this in mind, in this lecture we will be giving you a short briefing on the instrumentation of the neutron activation analysis technique also. The sequence of steps or processes happening during the most common type of nuclear reaction employed in the neutron activation analysis technique comprises of the following. Through non-elastic collision, the neutron interacts with the target nucleus, thereby resulting in formation of an excited state compound nucleus. The binding energy of the neutron with the nucleus results in the excitation energy of the compound nucleus. The compound nucleus, which is an excited state, then promptly de-excites into a more stable configuration by the emission of one or more characteristic prompt gamma rays. In most of the cases, it results in the formation of a radioactive nucleus, where decay happens by the emission of one or more characteristic delayed gamma rays, but at a slower rate subjected to the unique half-life of the radioactive nucleus. Depending upon the specific type of radioactive species, half-lives can have a range of fractions of a second to several years. The instrumentation of neutron activation analysis comprises of a neutron source. Different types of sources can be employed for this purpose. First, a nuclear reactor, an acetinoid such as californium, which emits neutrons through spontaneous fission, an alpha source such as radium or americium mixed with beryllium, this generates neutrons, a DT fusion reaction in a gas discharge tube. The instrumental components of neutron activation analysis also comprises of a semiconductor detector, associated electronics and a computer based multi-channel analyzer. If we talk about detectors, again there are various types of it which are being used in the neutron activation analysis technique. Most of them are designed with the intent to detect the emission of gamma radiation. The most common types of gamma detectors used in neutron activation analysis are the gas ionization type, scintillation type and the semiconductor type. Also there exist two conformations of detector. First one is the planar detector, which is used for PG neutron activation analysis, and the second one is well detector being used in DG NAA. The planar detector comprises of a flat and large collection of surface area that is placed close to the sample. The well detector surrounds the sample with a large collection surface area. The major advantages of neutron activation analysis, particularly instrumental neutron activation analysis, are the relative freedom from matrix effects and interference, high accuracy, very low or zero blank contributions. Since nuclear reactions and decay processes are virtually unaffected by the chemical and physical structure of the material during and after irradiation, the matrix composition has almost negligible effect on the induced activity. Biological materials have low neutron absorption cross sections unless high concentrations of elements such as cadmium and boron are present. Thus, neutron reduction in such samples during irradiation is very small and can be corrected if present. The gamma ray attenuation during counting of small volume irradiated biological samples in vitro analysis is also small, except at energies below 100 kilowatts, and can be corrected in the case of low energy gamma rays or large sample volumes, example in vivo NAA. The absence of matrix composition effects thus allows using standards that have different composition and even physical state from that of the sample. Interferences may arise through production of the radionuclide via fast neutron reactions on other elements or from coincident gamma rays during counting. Sample pretreatment is minimal in RNAA and INAA and involving only packaging the sample in an irradiation container, which can be quartz, polyethylene or aluminum foil. For ultra trace analysis, this is an important advantage over other techniques such as in AAS or ICP, in which the sample must be in solution form, thus potentially introducing contamination from reagents and equipment, maybe Planck problem, and the loss of analyte through adsorption, volatilization, co-precipitation, etc. After adding non-radioactive carriers to the radionuclide tagged sample, post-irradiation can be done in RNAA, eliminating blank contributions and chemical yield determination of the separation process, that is, to evaluate losses during decomposition or in separations. Dear students, after you have studied about the advantages of neutron activation analysis technique, we will now be studying about its application in various fields including that of forensic science too. Neutron activation analysis measures the total amount of an element even in extremely low concentrations, parts per trillion or even lower, in a material without regard to chemical or physical form. Samples analyzed can be liquids or solids and do not have to be put in a solution. Theoretically, every element can be neutron activated, yet some conditions are required. Firstly, the element must have an isotope with a high cross section that is able to fix the incoming neutrons. Secondly, if delayed neutron activation analysis is used, the half-life of the isotope has to be long enough so that the amount of activity is measurable. Third, the isotope itself must be relatively easy to get in sizable quantities. And lastly, gamma rays must be produced that are reasonably intense and in a limited energy range. Applications of neutron activation analysis includes environmental studies to characterize pollutants, semiconductor material analysis to measure ultra trace elemental impurities, archaeological studies of the distribution of the chemical elements and fossil materials. In forensic studies, as a non-destructive method, suspect chemical agents, pharmaceutical materials analysis to measure ultra trace element impurities, etc. Unfortunately, facilities for using this method do not exist everywhere. Evaluating the evidence, the result of subjecting a piece of material to neutron activation analysis is that the material is found to contain certain elements in the measured concentrations within experimental error. The next step is to determine the relevance of the result in solving legal issues. Sometimes the legal issue depends directly on the amount of a selected element in the material. For example, if the question is whether a particular death was due to arsenic poisoning, the activation analyst might measure the amount of arsenic in the victim's hair or in other tissues, and if the amount exceeds the normal amount by a considerable value, then death by arsenic poisoning has a high probability. In other cases, the legal issue is whether a given piece of evidence came from a particular source, that is the identification problem. For example, a hair found on the body of a victim might be compared in its trace element concentrations to the hairs of a suspect. Then the crucial question is the degree to which the comparison signals out the suspect as the guilty party. In neither of these cases is the neutron activation analysis evidence sufficient in itself. Additional data are needed to evaluate the significance of the chemical analysis done by neutron activation techniques. In the first case, it is necessary to know the normal amount of arsenic in the tissue or hair measured. Knowledge of the distribution of arsenic concentrations in hair of the living general population is required, so that one can calculate the probability that a person chosen at random would have an arsenic concentration equal to what was measured in the tissue or hair of the deceased. In the second case, more information is needed to determine how much more likely the hair found on the victim is of the suspect than from a person chosen at random from the general population. Although the detailed considerations are different in different type of cases, the analysis in each case depends on the existence of sufficient background information with which the evidence at hand could be compared. Only then the evidence can be interpreted properly. Complications of identification. A criminal often leaves some materials in the area of a crime, such as a shirt button or a hair from his head or any other part of his body, or he may carry away something from the vicinity of a crime, such as a hair of the victim or a piece of glass from a window broken in the case of a burglary. Although hair, for example, show similarity in the major constituents, there is great variation in the minor constituents from one person to another because of differences in diet, body metabolism, occupation and environment. Because of the great sensitivity of activation analysis, the question arises whether materials can be unambiguously characterized by the trace element concentrations. If it could be shown, for example, that every hair of a person's head was identical to every other one and that they were all different from the hairs on a different person's head, the procedure would provide an extremely powerful method of identification. Revelation of gunshot residues. Neutron activation analysis technique is used for revealing mineral gunshot residues. These gunshot traces, after picked up from the crime scene, are used as materials proofs for judicial investigations. Samples of metallic powder residue can be realized after several shots by different kind of weapons with local and foreign ammunitions. Like other instrumental techniques, neutron activation analysis is also an important technique in the field of forensics. The technique of neutron activation analysis is used both for the qualitative as well as quantitative estimation of the samples. The technique of neutron activation analysis is a nuclear process employed for the detection of the radioactive elements in the sample and their concentration. Determination with great sensitivity without the destruction of sample which is being analyzed. With all these information, here we come to the end of today's lecture. Do keep in mind what we discussed today. I'll be back with one more lecture in this series. If you want to learn more and enhance your knowledge, you may log on to our website www.cec.nic.in for multiple choice questions, quizzes and LORs, etc. Thank you for your time today. I will see you in the next lecture. Have a great day.